Thank you, viewers. This is Mr. Odingo. Today I want us to start a new chapter here, which is called Organic Chemistry. And we were not supposed to do this chapter right now, but we received a lot of requests from students that are very much interested in this particular chapter. So we are going to be able to try to do it so that they can simply be able to solve the problems that they have. I believe we are going to try to go slowly and much more detailed to be able to engage our learners so that they can be able to appreciate the importance of this chapter and also some of the basic ideas that they need to gain. Now, according to my review on the syllabus, I realize this chapter probably requires about 45 lessons. That is from Organic Chemistry 1 to Organic Chemistry 2 in Form 4. Now, those 45 lessons are too many, so we are trying to be able to summarize so that actually we don't go there. Maybe we can have around 15 lessons, that can be all right. So, Organic Chemistry is a very enjoyable chapter, because why I say Organic Chemistry is a very enjoyable chapter is because it doesn't involve a lot of things we don't know. It involves actually many things that we interact with on daily basis. Now, the word organic here tells us that actually what we are going to deal with here are things in living things. Living things mainly plants, plants and animals. There are other living things, but these are things that we can see on a regular basis. So when we talk about organic chemistry, probably we're going to talk about those elements that we know are found in living things. We know that there are many other elements found in living things that are not considered organic. For example, iron, metal, we have magnesium, we have calcium. Those are not really considered organic, although they are found in living things. What we are going to basically look at under organic chemistry is to talk about those elements, the major elements that are found in living things, that is probably carbon. Carbon is one of the primary elements in the living things. Now, organic chemistry has been defined before as a branch of chemistry. Organic chemistry is being defined as a branch of chemistry, a branch of chemistry that deals with the study of carbon compounds except oxides of carbon, and oxides of carbon, carbonates, and carbides. Now, you realize that we know that we are talking about organic chemistry dealing with the study of compounds of carbon. Compounds of carbon or carbon compounds are very many, and they include oxides of carbon like carbon dioxide, carbon monoxide. We also have salts, that is carbonates, and other salts, carbide salts, probably calcium carbide and so on. Now, these ones are excluded when we are looking at organic compounds. These substances we are talking about here, oxides of carbon dioxide, carbon dioxide, carbon monoxide, carbonate salts, and also carbide salts, those are excluded under the study of organic compounds. So we are going to look at organic compounds as any other compound other than these three groups of compounds I'll be able to mention here. Now, it means therefore that we are looking at organic chemistry from the reference point of carbon. It means that carbon really here is very key. Carbon is very, very key. It's the primary element in the study of organic chemistry. So it means that these organic compounds we are going to talk about, some of them exist naturally. and some of them are synthetic, meaning some of them are manufactured by man, others are existing naturally. Some of the compounds that exist naturally, these organic compounds are substances like carbohydrates. We know carbohydrates in our bodies. Other than carbohydrates, we have proteins. We have lipids. These are some things we know from our biology lessons. We also know about things to do with nucleic acids, for example, the DNA and the RNA. Nucleic acids, this is where we have the RNA and the DNA. All of these things and many others like vitamins and so on, those things carry with them carbon. Carbon is the primary and the most abundant element in these particular compounds. And so these compounds are some of the natural organic compounds that we know. Now, we want to start looking at organic chemistry and what we are really going to entail as we move on. Organic chemistry is fairly wide, but at this level of secondary school, we are going to talk about things not too much extensive. And we are going to have around probably six homologous series. So you want to know, before I look at homologous series, I want to talk about carbon. Carbon is an element we know, number 6 in the periodic table, having electronic configuration of 2,4. So if carbon has electron arrangement of 2,4, it means that the outer energy shell of carbon has 4 electrons. This means that carbon can form covalent bonds with 4 other atoms around it, meaning that it can maximally, a carbon must form a total of 4 bonds because of the presence of these 4 electrons in the outer energy shell. So this one tells us that carbon can bond with other elements. For example, hydrogen. If I say this is bonding with hydrogen here, then we have this hydrogen here. If we say that it's bonding with chlorine, it will be carbon bonding with chlorine in that particular manner. So you see that carbon can form a total of 4 bonds around it, and those 4 bonds could be bonded to other elements or other carbon atoms. And that's why we have diamond and so on. So let's look at, again, another thing about carbon. Being that this covalent bond that it can form here, carbon can also be very unique to form different levels of bonds. For example, it can link between one carbon to another carbon using what we call single covalent bonds. Carbon can also form a double bond with another carbon atom, and also can also link with what we call a triple bond to another bond. So the possibility of carbon forming bonds, covalent bonds with other elements, is a very key property. That's why when we talk about carbon compounds, we are going to talk about, they could be compounds of halogens, bromine, chlorine, and so on. Hydrogen is there. We could also have nitrogen, and so on, and also oxygen, and as we go there. Another thing is here. Carbon can form unique bonds here. We see a single bond between the 2 carbon atoms, meaning a carbon and a carbon can link together. And a carbon can also link to another carbon using double bond. A carbon can also link to another carbon using a triple bond. This is going to be a very key thing, especially when we are categorizing these particular compounds that form this particular double, single, or triple bonds between each 2 carbon atoms. Now, if I come back to here, this particular case here, being that these carbon atoms can link with each other, it means that it's possible that a carbon can link with another carbon or many other carbon atoms to form either what we call rings or chains. Rings or chains. I believe we understand what a ring is and what a chain is. A chain probably is something probably long, not connected. For example, if I say this one, this carbon connecting to this carbon, connect to another carbon to this way, and then the other bonds are connected to hydrogen. This one is a chain. We see that there's a chain of carbon atoms here that are forming. You can see 1, 2, 3, 4. And this chain can continue if you have more carbon atoms to link. But another thing also is that these carbon atoms can also be able to form a ring. For example, if I have these 4 carbon atoms, they can also be bonded in this particular manner. So in this case here, these carbon atoms have formed what we call a ring. You realize that they are joined in a manner that they are forming something like a square. They are moving round. Each carbon is connected like that. So it can form a chain when they are joined in a very straight line, or maybe in a way that the 2 carbon atoms, the ends, don't really meet. But in this case, the 2 last carbon atoms come together to form a bond again. So this one we are talking about a ring. You can imagine what we call finger rings. This one also is a chain. So this possibility of rings and chains forming is due to carbon being able to link with another carbon atom, and also being able to accept to bond with other different elements. And we have seen here we have carbon, 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 carbon linking, but again they are also linked with other. You realize that every carbon atom here has a total of 4 bonds. That is because carbon can make a maximum of 4 covalent bonds, because it has 4 electrons in the outer energy shell. So carbon is very key in our case and very primary in organic chemistry. Now I want to go forward to bring in what we call classification of these organic compounds. Classification of organic compounds, we are going to talk about something called homologous series. So when we want to talk classification of organic compounds. So if you want to classify these organic compounds, we are going to classify based on similarities that they have. Just like we know, if you are in a classroom, you can classify the students based on gender. You can say girls and boys. When you take girls and boys, you are using similarities here, and what you are using to differentiate these 2 groups is gender. You can also classify students in a class as tall and short. That's another way. You can also talk about brown, black, and those are different classifications you can use to group them. So we are also going to use other modes of classifying these organic compounds. Like I said, in our level here, we are going to have probably up to 6 classifications, or really 5 major ones. And to classify these things, we are going to use what we call functional groups. Functional groups. So a functional group is going to enable us classify these compounds into what we call homologous series. Homologous series. So what is a functional group? Before we actually see what are our homologous series that we have, what is a functional group? A functional group is said to be an atom or a group of atoms, an atom or group of atoms responsible for the chemical properties of a molecule, or could be of a compound. So a group, an atom, or group of atoms, sometimes you can say is a part of the molecule that is responsible. But now we say an atom or group of an atom that is responsible for the chemical properties of a molecule. It means that chemical properties are meaning chemical reactions. We know we have physical properties, which are actually things we can see or measure or taste using our 5 senses. Chemical properties are things that involve chemical reactions. Now, the part of a compound that is going to determine the chemical reaction or chemical properties of a compound is what we are going to refer to as a chemical or a functional group. And those set of compounds or those set of molecules that will have similar chemical properties will be referred to as homologous series. Now, I want to give some of the homologous series here that we are going to deal with. One of them is, number one is alkanes. 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 Number two, alkenes. Number three, alkynes. Number four, alcohols. Number five, alkanoic acids, also called carboxylic acids, alkanoic acids. This one can also be referred as alkanols. Alkanols. This can also be referred as carboxylic acids. Now, lastly, and this may come from the number 4 and 5, is esters. It's also a separate group of organic compounds that we'll be looking at. Now, you realize that in your course of your study, we are going to talk about this homologous series. 1, 2, 3, 4, 5. I say this one, I kind of want to separate it because it also has a separate or a unique functional group here. So we have 6 of them, and you realize that these 3 ones here, usually we refer to them as hydrocarbons. The other ones are not hydrocarbons. We are going to find out later what hydrocarbon actually mean. Now, these are homologous series. We said we are going to group them because they have the same functional group, and being that they have the same functional group, they are going to show that they have the same chemical properties. And so, what is the functional group of alkanes? Usually, this is a very debatable question. For scientists have been arguing over what the functional group of alkane is. But all of them come to conclude that the functional group of alkane could be just a single bond between carbon atoms. So any compounds with single bonds, between carbon atoms is going to be called alkane. The end word here is ANE. So ANE in organic chemistry refers to, tells us there's a single bond. Single bond. So we can actually see that whatever compound ends with the suffix ANE, that one is something that has a single bond. And if it's a single bond, then the full name should be alkanes. Because realize that the prefix alk is almost everywhere until probably here. So if it is alk, they are similar here. So the only thing that will differentiate these compounds is these parts of the name here, going the other side. This one is ANE, ENE, YNE. So let me remove this S, maybe S kind of confuse us. YNE, ANE, ANE. So if you have ANE, I said, it refers to single bond. It means that that single bond should be its functional group. And not just single bond between carbon and another element. It must be single bond between carbon atoms. What about if we go to alkenes? Alkenes here, they have double bond, Lana. So double bond between carbon atoms, because we said that carbon was unique. It can form bonds between itself, and between itself, the bonds could be a single, double, or triple. If you look at this compound here, this is its functional group here. So the presence of these double bonds between the two carbon atoms signify that that name should end with ENE. So ENE here should tell us that that is a double bond, and that one falls under another different homologous series. This single bond is also a separate homologous series. Alkynes are triple bonds between carbon atoms. So this alkynes here is another homologous series. The name ends in YNE, or in other words, ine. This one is in, this one is N. So sometimes students get mixed up with N, in, ine, because you can find a compound which is probably, let me say, ethene. Then another one is, let me start with ethane, ethine. So you realize that you can think that this is one compound. Probably if you are finding a book you may want to correct, maybe you think there's a mistake. But these are actually totally different compounds. This one you expect to find single bonds between carbon atoms. This you expect to find double bonds between carbon atoms. This one you expect to find triple bonds between carbon atoms. So this one also is a homologous series. Then alcohols, or what we call alkanols. Alcohols is what we know in the streets. People say alcohol, and when people talk about alcohol out there, they only know about the one people drink, those ones who get drunk out on the roads, as I've drunk alcohol. Alcohol is a common name for a group of many alcohols. And this is the common name that people know. Alkanols, probably the scientific name. We are going to see that later on. So alcohols, the functional group is not coming to the carbons, but on the end of a compound. You realize that when you talk about the first three groups, the functional group, we are defining this functional group based on the carbon atoms. But when you come to alcohols here, we are now talking about a functional group which is actually going to exist part of a compound outside the carbon atoms. Now this is OH. When you see a compound with a functional group OH, an oxygen and hydrogen atom existing, then you know that one is an alcohol. And alcohol, their names end with "ol." For example, ethanol, butanol, propanol, that is what we call alcohols. So it is also another homologous series. Then when you come to alkanoic acids, this alkanoic acids is also another homologous series. And alkanoic acids, they say they have COOH. Sometimes we say Cu. So COOH, any compound with COOH. Sometimes when you say C there, when you see clearly, this is what we call, sometimes it can be given like this or it can be given like this. You need just to understand that both of these, this displayed formula, this is actually just part, probably what we call structural formula, showing the atoms, the way they are arranged there. So this one here also is another functional group, and this one, the name ends with oic. Oic. So anything that when you read it ends with oic, that is carboxylic acid or alkanoic acids. Anything that when you read its name it ends with ol, that is an alcohol. Anything that ends with "ine", that is alkynes, that is ends with "ene", alkene, and "ene", alkanes. You realize that the ends of this name will already tell which functional group is there. If you read "ene", you know there's a single bond between the two carbon atoms. If you read "ene", there's a double bond between the two carbon atoms. If you read "ine", there's a triple bond between the two carbons. If you read "ol", there's OH in that particular compound. And then if you read "oic", you know there's COOH in that particular compound. Then finally, if we have, I said this is also homologous series. We have esters here. Now, we are going to see later on that esters are actually compounds formed when alcohols and alkanoic acids react. So, even though it's going to be a compound derived from two other homologous series that is there, it also has its a unique functional group, and the functional group is this one. This is the functional group of esters. So if you see something like this, it is an esters. It's an ester here. This is a functional group of ester. So these are functional groups we are going to look at in the course of our study in this particular lesson here. Now, we have talked about what is homologous series. What is now an homologous series? We said that they have all things that have the same functional group can be referred to as homologous series. For example, if you have alkanes, we know someone may think is one. You see, if you put this mark here, it means that this thing can be a link chain. This one can also be another chain going. This can be, they could be big molecules, but you start with a smaller one up to a bigger one. So whether the smaller one or a bigger one, just like we have whites, you can have a white who is 2 years, 3 years, 10 years, 100 years, is still a white man. You have a black, it's also a black man. That is also, you can talk about that is a grouping of human beings on in this world. Now, This is the definition of a functional group. We have said it's an atom or a group of atoms responsible for the chemical properties of a molecule. So alkanes here have the same chemical properties. Alkenes, the same chemical properties. Alkynes, the same chemical properties. Alcohols, the same chemical properties. Alkanoic acid, the same chemical properties. Esters, the same chemical properties. Although physical properties will not be the same, but physical properties will show a gradual change. There will be a trend in the property. If it's density, you expect density to increase from one molecule to the other as the size increases. Now, what is homologous series therefore? Homologous series therefore here we should refer to it as a family or a group. It's a family actually because it's a collection of very many molecules that have the same chemical properties. So, we are going to say that homologous series is a family of organic compounds, family or group of organic compounds, with the same chemical properties, same general formula, and shows gradual change and shows gradual change in their physical properties. Now, if I ask you what homologous series is, even if you tell me that it's a family of organic compounds with the same chemical properties, I would just be satisfied. But you can continue to give all these things. Now, before we lose the idea about what homologous series is, I want us to come to what we call features of homologous series. When you know features of homologous series, then definition of homologous series will not be hard. So I want to start from what we have there. That is features of homologous series. Features, properties. So features of this homologous series. When I talk about number one, we say that they have the same chemical properties. So have, or we can say members of the same homologous series, members of the same homologous series have the same chemical properties. Good. We said that if a homologous series of the same functional group was responsible for the chemical properties. So it means that all members of alkanes, for example, will have the same chemical properties. All members of alkenes will have the same chemical properties. That's what we mean here. That all members, we said these are homologous series. So all members of each of these homologous series have same chemical properties. And we are going to see that one as we look at each of these homologous series one by one. Number two, we have mentioned something here, that they have the same general formula. So members of the same homologous series have the same general formula. Now I want to go back and explain number one. Members of the same homologous series have the same chemical properties. Someone may not be understanding what I mean by chemical properties here. It means that these members react the same way. For example, if I take a group of alkanes, so I take alkanes and I want to burn alkane. For example, now the first member of alkane, we are going to see this later on, is methane. The second number is ethane. We are going to see this one, don't worry. The third number is propane. Now, if I have these members of these groups, methane, ethane, propane, butane, pentane, hexane, as you go like that, when you burn them in oxygen, water, and carbon dioxide gas, water and carbon dioxide gas, that's what you are going to get if you react any alkane, if you burn any alkane in oxygen. So that is telling us that if the product you are getting is the same, then this could be, the reaction is the same. The property, that property of burning them in our air is the same. What about if you react them with chlorine? When you react with chlorine, they will always form what we call chloroalkanes plus hydrogen chlorides. So you are going to see that happening for every ethane, every alkane, whether it's ethane, methane, propane, butane, pentane, decane, and so on. That's what we mean by chemical properties, that they react the same way and they produce the same products. General formula. Let me come to this general formula here. I've written some members of alkane, the first three members, that is methane, CH4. Then I wrote ethane, C2H6. Then I wrote propane, C3H8. I want you to know that every time these formulas conform to a certain rule here, that if carbon is 1, for me to get hydrogen here, I multiply the carbon by 2. So 1 times 2 is 2, plus 2, I get 4. So this one, 2 times 1 plus 2. If carbon is 1, this is hydrogen. What about if you have here, carbon here is 2. If you take 2 by 2, we get 4 plus 2. Here carbon is 2. Here if we have here carbon is 3, we'll say carbon is 3, so we'll say 3 times 2, then plus 2. You realize that in each case here, the first one, we took the number of carbon atom, which was 1, we multiplied by 2, that is 2, then we added 2. We get 4 for hydrogen here. Here, if carbon is 2, we multiply 2 by 2, we get 4. Then we add 2, we get 6. That is the number of hydrogen atoms if you know the number of carbon atoms. In this case here also, we have the carbon atoms is 3. We multiply 3 by 2, we get 6. Plus 2, we get 8. So it means that if we know the number of carbon atoms, we can actually determine the number of hydrogen atoms using this relationship. So if this one here, this one here is N. So N here is, this is N, which is 1. This is N, which is 2. This is N, which is 3. This is N here. Let us be able to get an unknown molecule with the number of carbon atoms N that we don't know. So it means that if we know the number of carbon atoms is N, for us to be able to get the number of, this is number of carbon atoms. For us to get number of hydrogen atoms, what we need to do from what we have done here, we took this one, this was our N. We are multiplying by 2. Every one, we are multiplying by 2. So it means that for us to get the number of hydrogen atoms for alkanes here, we need to be able to multiply N by 2. So 2N, then plus 2. So it means that the number of carbon atoms for an unknown molecule in alkanes is N, and the number of hydrogen atoms should always be 2N plus 2. So if I'm writing a general formula here, it will be CNH 2N plus 2. This is the general formula. So it means that all alkanes will have to conform to this particular general formula. All of them. That is what we mean by that. All members have the same general formula. Number three, what I want to also mention here, the third feature of homologous series is that the third feature here is that members of the same homologous series, members of the same homologous series, have members of the same homologous series have, no, I need to change this writing. It's called consecutive members. Consecutive members differ. Consecutive members of the same homologous series of the same members of the same, to include that, of the same homologous series, same homologous series, differ homologous series differ by CH2, differ by CH2 unit. So you realize that, what does that mean? Let me explain once more what that means. Consecutive members meaning members following each other. For example, I just drew some here. I wrote CH4, that is methane. We are going to see this later, so don't worry about what I'm saying. Just look at what I want to do. And then the third one is C3H8. So these are consecutive members, methane and ethane. These are consecutive numbers. Let us subtract the difference here. Carbon is 2, carbon is 1. So 1, 2 minus 1 is carbon, 1 carbon. Then hydrogen is 6. 6 minus 4 here for hydrogen on this other side is 2. So hydrogen is 2. This is what we mean here. So the difference between ethane and methane is CH2. What about the difference between ethane and propane? These are also consecutive members. What we are going to do here, carbon atoms, 3 minus 2. C3 minus C2, we'll get C1. Then H8 minus H6, we get H2. So you realize that again here, if I remove this one, again here, that will continue. So it means that if I wanted to get the next one, it's like series and sequence. If I want to get the next one here, what will I do? I will simply add this one. It must be CH2 here. I will simply add this one here, and I say 3 plus 1 is 4. So C4 here. H8 plus H2 is H10. And you can continue like that. It's a series and sequence because the difference is actually common difference in what we know in series and sequence. So that's what we mean by the consecutive members of the same homologous series differ by CH2 unit. Let's move to the fourth one. The fourth one is that members of the same homologous series have the same method of preparation. So we say members of the same homologous series have the same method of preparation. Good. Method of preparation, this is very direct, that if I want to prepare methane, I want to prepare ethane, propane, that I should use the same method. That is very, very direct, that I should just use the same method if I want to prepare this, and this. The method of preparation is the same. That is very self-explanatory. The last one here is talking about the physical properties. So you realize that everything has been the same. Here only we don't have the same. This one here is going to take a different turn. So we are going to say members, the physical properties, of a homologous series, show gradual change. Gradual change, or I can say a trend, a gradual trend. Now, it means they are not the same. And these physical properties, I said physical properties in chemistry refers to things that we can detect using our 5 senses. Other than detecting using our 5 senses, we can also use some equipments to measure. For example, I can measure the length, I can measure density, I can measure mass, I can measure temperature, I can measure. So things that can be measured or things that we can see, taste, hear, smell, touch, those are things we refer to as physical properties. And those physical properties, for example, let me look at a few, just an example. For example, density. So we cannot assume in our right minds that the density of methane is the same as the density of ethane, is the same as the density of propane. That is crazy. Reason is, we know if you have done moles now, you have done moles in Form 3, you understand what we call molar masses. The mass is a factor of density, because density, if I remember very well, is given by mass over volume. That's what density is. So it means that density is obtained from these two things. And you can see that density here is directly proportional to mass. It means that density is directly proportional to mass. So it means that the bigger the mass, the bigger the density. Now, using the concept of molar masses we have learned in Form 3, you can therefore agree with me that the mass of this thing here, carbon, is 12, plus hydrogen is 1 times 4 is 4. So 12 plus 4 is 16. This is the mass per mole of this particular compound. The mass per mole here is, this is 12 times 2, 24. 24 plus 6. So 24 plus 6 is 30. So this is 30 mass per mole. This one here is 36. 12 times 3 is 36, plus 8 should be around 44. So if you have these particular masses, we expect from what I've said here that the mass and density are directly proportional, that this one will be the less denser one, this will be the most dense, the one with the bigger density. So it means that therefore, coming from the first member to the third member, density increases. Density will increase here. That's what we say, that it shows a gradual change. When I come to melting point, I expect here propane to have a higher melting point. Why? We talked about bonding and structure, especially covalent bonds. And this one is a simple molecule, so it is having what we call simple molecular structure. And I said the simple molecular compounds, their melting point will increase with the increase in the molecular mass, meaning that the weak van der Waals forces here and here and here are not the same. So the sum total of the interactions of the force of attraction, the molecules of methane here, compared to this, compared to that, the bigger the molecule, the stronger the covalent bonds. The stronger the covalent bonds, the higher the melting point. So we expect that the melting point will increase from here to here to here, meaning the melting point of this will be higher than this. And the melting point and boiling point of this will be higher than this. So there are many properties we are going to look at. If you look at probably at alkanes, we'll discuss this. We go to alkenes, we'll discuss this. Alkynes, we discuss this. Alcohols, each of them, we are going to talk about this particular trends. But what we have to know that the physical properties of homologous series show gradual change or some trend in this particular. They could be decreasing, they could be increasing. So, but they must be changing based on the increase in size or decrease in size of that particular molecule. Now, viewers, we have learned, we are still doing what we call introduction to organic chemistry. We are looking at the basic things we are going to see across all these homologous series I listed here, from alkanes to esters down the line. Now, I want to move to the next thing, which we call formula in types of formula that we are going to meet in organic compounds. Types of formula. Now, types of formula, types of formula. There are many formula we are going to meet along the way, and this formula here, they are going to help us to answer questions, so they can also be used to show us its names and formulas. You could be told to give a name, you could be told to give a particular formula of a compound. So the first formula here is going to be what we call displayed formula. Displayed formula. Now, those students who take KCSE, their syllabus is not very much talk about displayed formula. But I want to invite your attention to understand that displayed formula is one of the formulas we are going to meet in your studies. And the displayed formula is a formula that shows all the bonds and all the atoms, all the bonds and all the atoms separately in a molecule. Good. So displayed formula shows us two key things. It is showing us all the bonds very clearly. Then it shows us all the atoms in a compound separately so that we can see them clearly without anything being hidden to us. And if I talk about that, if I say this one here, this is what we call butane. If I do this, this is what we call a displayed formula. In KCSE, this formula usually, I think, is mostly just referred to as structural formula. But today I beg to show the difference between structural and a displayed formula. So this is a displayed formula of what we call butane. We are going to see how to arrive at that particular name. We see all the bonds here. All the bonds between each atom is showed to us. That's what we call it, displayed formula. And we can tell that it's showing us two things, all the bonds and all the atoms separately in a molecule. The second important formula here, now let's go to the structural formula. Structural formula. And the structural formula shows us how atoms are bonded to a particular carbon. Shows, it's a formula that shows how atoms are bonded. Basically, it will tell you that which carbon atoms has how many hydrogen atoms, like in our case here. We can see that we can transform this displayed formula into a structural formula. For example, I can simply say the first carbon atom has three hydrogen atoms, so I'll say CH3. Then I can put a bond here by indicating this bond. I say the second one has two hydrogen atoms, you see. The third one also has two hydrogen atoms. And the last one has three hydrogen atoms. You see, 1, 2, 3. This is a structural formula. We can also show it this way. Or it could be CH3, CH2, CH2, CH3. This is another way of writing a structural formula. This is another way of writing a structural formula. We realize that in this formula here, what we have indicated is that it's showing us to which carbon atom has how many hydrogen atoms. Like in this case, the first one has 3. The second one has 2. The third one has 2. The fourth one has 3. Now, you realize that between this formula and this one gives us much more information than this one. So the displayed formula is much more conclusive. You can determine how many atoms are there. You can tell us how they are bonded and also clearly indicate which bond is connecting what to what. Now, the third formula is molecular formula. Molecular formula. Molecular formula is a formula that shows the exact number of atom of each element in a molecule. So here, this formula is going to hide certain things from us. We will not know which carbon is bonded to what and what, but it's just going to tell us how many carbon atoms are there, how many hydrogen atoms are there. And there's going to be C, like in this case, how many carbon are here? 1, 2, 3, 4. So we just say there are 4. Hydrogen, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So hydrogen atoms are 10. This is what we call the molecular formula. Basically, what we can see from this formula is that we have 10 hydrogen atoms and 4 carbon atoms. That's what a molecular formula will tell us. And then the final formula I want to talk about today is what we call the empirical formula. Now, if you did moles earlier in Form 3, you already know what molecular formula or how you can determine it, how you can determine empirical formula and molecular formula from calculation, from empirical data given to you. Now, empirical formula is the formula that shows the atoms of each element in a simple whole number ratio. So we say that shows atoms of each element, atoms of that shows atoms of each element, that shows atoms of each element in whole number ratio. In whole number ratio. So if we have empirical formula here, you raise the ratio here of carbon to hydrogen is 4 to 10. So let me say the carbon to hydrogen. Carbon are 4, hydrogen are 10. That's according to the molecular formula. Getting the whole number ratio here, it means we can simplify this one by 2 here, by 2 here. So we can say this is 2, this is 5. So empirical formula of this particular butane here will be C2H5. This is now going to be our what we call empirical formula. So if you have a molecular formula, you can get empirical formula. Sometimes the empirical formula and the molecular formula are the same. For example, if the number of carbon atom is odd, for example, if I say C3H8, this only affects alkanes. If the number of carbon atoms is odd, it means that the empirical formula and the molecular formula are the same. This is propane. But if it is even, for example, if I say C2, that is ethane, H6, here the number of carbon atom is even. So we are going to have, simplify this one, 2 here 1, 2 here 3. So the empirical formula will be CH3. You realize that it's telling us the ratio of carbon atoms and hydrogen atoms in that particular molecule. Now, this is what we have in organic chemistry. We have a fifth, what we call a fifth formula, which we are not going to use in our level of study, is called skeletal formula. The skeletal formula shows the opposite of structural formula, because structural formula was only showing us how atoms are bonded. For example, it shows us each atom per carbon atom. But in this case, it only shows us the bond between the carbon atoms only. For example, you can have this one, 1, 2, 3, 4. So we are just having 1, 2, 3, 4. You realize that this one here is a carbon atom, this a carbon atom, this a carbon atom, this a carbon atom. So it will actually go like that. So you realize that these corners, they represent a carbon atom. This represent the bonds. You realize that if this is a carbon atom, they don't tell you how many hydrogen or whatever elements that was used to bond here. If it is hydrogen, it's not indicated. But if chlorine or something else, it will be indicated for you there. So that's a skeletal formula. And for this lesson that we are having now, we are not going to talk about that one. Now, viewers, after understanding what formula in alkanes are, we have actually now finished what we call introduction to organic chemistry. Now, to be able to effectively explain to you organic chemistry, I'll be able to divide organic chemistry into 3 parts. And these 3 parts, I'm going to be able to separate them so that I refer to them as organic chemistry 1, 2, and finally 3. So my classification or my groupings based on how I want to cover them will be based on organic chemistry 1, and organic chemistry 1 will be we'll be talking about hydrocarbons. Hydrocarbons here, we expect under hydrocarbons to talk about 3 or 4 areas. A will be alkanes that we have seen, the Homologous Series. B, under alkanes, we are going to talk about crude oil. Then we'll talk about alkenes. Then we'll talk about alkynes. Then we are going to finish organic chemistry 1. Organic chemistry 2, we'll talk about alcohols, alkanoic acids, and esters. That's what we are going to talk about under organic chemistry 2. And then organic chemistry 3. and Organic Chemistry 3, we are going to talk about detergents and polymers. Detergents like soaps and polymers. So viewers, this is how we are going to separate this part, and I said that we are going to say this lesson according to your syllabus requirement. You need to cover it in 45 lessons. That is 25 for Organic Chemistry 1 and these two 20 lessons. But we are going to try to ensure that we put it together in a way that in the first here we have like 4 lessons: alkanes, crude oil, alkenes, and alkynes, if possible. Then we have alcohols, esters and acids. Alcohols 1 lesson, alkanoic acid another lesson, esters another lesson. Detergents here, detergents 1 lesson, polymers probably another lesson. It will be a hard task to do, but we are going to try, and everything will be clear as we start them to see what's the load of each work, so that we can break them based on what is suitable for us. Now viewers, that is all for introduction to organic chemistry. I hope it was very clear. Please subscribe to our channel so that you can be able to enjoy our free lessons. Thank you very much, and